Hi mentors, welcome to Plinko Probability. So let's start with the intro. And so this is a multi-step experiment, random experiment. Each step is binary. So what this means is that you can go either to the right or to the left in each step, but then it's multi-step. So the actual number of outcomes will be more than two. Right, left, right, etc. It lands on this tube almost in the middle. Another run of the experiment. This ball kind of makes binary decisions at each step, decides, so to speak, to move either to the right or to the left. And so, yeah, at the start, you can just show this experiment. You don't even need to say that there's a 50-50 chance to go to the right or to the left. And then you ask students to actually draw a baby version of this and just predict the number, the counts, right? How many will land on each tube. So this is the intro. It's just an introduction. Then you can go to the lab. And so what happens in the lab is that you have several parameters. So first, the number of rows, which means pretty much how many outcomes you'll have. So one row is just two outcomes. So this is just equivalent to tossing a coin, right? Left, right, tails, or heads. And so let's experiment a few. So left, right, left, right. As you can see, I can keep track of the count. So this is the same experiment, just run several times. If you click here, you'll see it as a fraction. So that's pretty useful. 3, 5, or 0.375, 0.625. You keep tossing or keep dropping these balls. And then there's something called ideal here, which is the equivalent of the true probability. Now here's the ideal frequency, so what you would expect. And so these blue rectangles actually tell us what we should expect. So thus far, it's not going the way we expected. But of course, if we keep dropping balls, then the red count, meaning the fraction, both of them will approach to 0.5. So another, let's restart here. And okay, let's put some sound. Another thing you can do is make it uneven, right? So make it unfair. So for example, you could have a probability of 85 of going to the right. And then you can start, dropping some of these balls. The ideal is here. So this looks good already, but you can keep going and see what happens. Again, you can do it as a fraction. You can always erase and restart here, etc., etc. Okay, of course, this was done in previous meeting, just tossing one coin. So it's not as interesting as putting more rows. Let's put more rows. Okay, 12 is too much to start. You could start maybe with 3 rows, and then you could ask how many outcomes are here. Students should note that there are actually 4 outcomes because there's 3 rows. And so what will happen is that the beans would be here, 0, 0, 0, 0, thus far. You could make it more interesting and say, okay, let me tilt this a little bit to the left, so slightly, so that there's now a 0.45 probability of going to the right. So it's more likely to go left, as gravity suggests, so to speak. So these balls are slightly more likely to go to the left. And so ideally, you would expect these to happen. So the shape of the frequencies, as in meeting 3, it's still a mountain, still some symmetry, but it's leaning more towards the left. Of course, if I change it more, and let's say now I really want to go left, so let's say at 0.2 probability of going left, then you'll see that it's pretty likely to get in the leftmost bin. And we can see that by experiment. It's very important that you experiment, that students see that it's gonna be actually the case. And so that's how it goes. You can pause at any time. Let's pause, for example, here. So n equals 84. So from these 84 balls that we've dropped, we have 43, 35, 5, and 1 in these 4 bins. And so this is pretty, it's pretty consistent with the ideal probability. Let's go wild and actually do something like 20 rows. So there's, lots of outcomes. So there's 21 outcomes from 0 to 20. And so you could do fraction, or you could keep in count. And then you could ask students to, predict if I drop 100 balls, what's gonna be the shape of this frequency graph, of this bar graph or histogram for these, And so students may predict that there's some symmetry, but what about if you tilt it? So if you start with 0.5, okay, let's try, and let's just be a little patient and see what happens with all these balls. So it's very important that students get the intuition that it's really, really hard to get to the extremes, because that would mean just going right, 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 right all the time, or left, left, left all the time. Whereas getting in the middle, there's several ways, just combinations of left, right, and the picture, clearly shows that. Let's compare to ideal. So you still have to wait for them to almost match, but with patience, you do. So this is simple in terms of a fair step. Each step is fair, so 50-50. But what you can do now is maybe tilting it, let's do 75, tilted to the right. And so you can ask, students to predict what's gonna be the shape of this curve. And so kids could predict, you could annotate for them, or they could, chat and you write for them. Some may still predict this type of curve, but some may say, okay, since this binary probability is, more tilted to the right, so there's a 75% chance of going to the right in each step, then it's probably, very unlikely that we land in the left. And then kids could maybe do, predict something either like this, or, maybe something even more extreme, something like this. And so you can experiment and, just see what's going to happen from the experiment. You can also show them the ideal after. And so right from the start, we see that it's really hard to get into bins 0, 1, 2, 3, 4, and even 5. And so you get a sense of a center, and the center seems to be, the tube or the bin number 9. And at some point, you can actually show the ideal frequencies, so meaning the expected frequencies, if we did this experiment infinitely many times, so to speak, and it confirms that bin number 9 is really the center. And so the preferred tube is this. So if you were to bet on a single tube, you would bet on this one. And then, it's like a mountain, so there's some symmetry. So all these guesses we did were, sort of correct, but we could have just guessed something like this. So let me annotate. And so what turns out to be the winner is a mountain like this, right? So with a center in number 9. And then you can reset and say, let's stop, dropping balls for a minute, and let's just focus on the ideal frequencies and see how this shifts. So if you start with a binary probability of 0.5, then it's clear that the center is 6. So, right, because you don't have any preference of the center will get most of the outcomes. Changing the rows doesn't really have any effect on the shape. It's still a symmetric mountain. It's just more in detail, so to speak. But what really changed is changing the binary probability at each step. So let's say I shift it here, and then you see how this mountain starts changing. And I think it's really important to do this experiment of shifting the binary probabilities, maybe putting more rows so that we see more detail. And then doing this experiment like this. So you see this sense of moving, right? This sense of flow, something like sort of like a domino effect. And also consider the extreme case in which the probability is just 0%. And so there's no chance that you're going to go to the right, you only go to the left. So this means there's just only one path, just one outcome. And so the total count, well, it's just all of them go there, right? No matter how many you toss, it's impossible to get out of this bin. So this is just some trivial extreme case. And those cases are really important to consider because, that will tell students what they can expect, as the worst or as the best. So it's important for them to gain the intuition. And then you change it, right? Then you start changing and you run the experiment again and see what happens. Just one last note, this has sound. And so sound is good. It can be a little distracting, but it's also kind of peaceful and relaxing. And you could say that it's like a melody, right? Just tossing one. Let's wait for these balls to land. Just tossing one ball. Let's hear the melody. And so this is like a monkey or any animal, even a human or a cat, playing a piano with only two keys and just randomly choosing, right? And that's pretty much what we're doing as far as the binary experiment. What happens, of course, is that then we need to see what's the combination of these keys to see where we land, and different melodies will actually land in the same, in the same bin or in the same tube. So this feels like a tree in the process, but it's not a tree in terms of the results because, and let me annotate here, you could have two different balls that follow very different paths. So for example, here, as one ball, and the other ball could be maybe this, something like this. So very different paths, right? Nothing to do. But then at the end, they end up in the same bin. And so they started pretty different. They end up being the same outcome, the same result. So a tree doesn't do that, right? In a tree, whenever you split or make a different decision in one step, then forget about being equal. You have different outcomes. You are different. But here, this is not the case. And that's what leads to this symmetry, because you could have more likelihood in these bins in the middle because there's just more ways to get there, right? So going back to the, binary probability of 0.5, so going back to this example, which is really, I think it's really important to always go back to this fair example. Then what we're saying is that it's really hard to get this type of outcomes. There's only one way, left all the way. Same for this type of outcome, just one way. So those are really, really unlikely. But then to get to the bins in the middle, and for instance, let's just analyze this one, there's several paths that could lead you to there. Several ways, lots of ways, and you can count them, but this is not the purpose of this meeting, of course. We already did some counting in previous meetings. This is more to build the intuition of what's going on. So hopefully you enjoy it and have fun. Thank you.